So today's speaker is Kadri İlker Berktav from Bilkent University. So he's going to tell us about homotopy theory of stacks and higher structures.
Yeah. Thank you. Thank you for the introduction and having me here. So essentially, as you said, we are going to discuss, homotopy theory of stacks, and then I will briefly mention more generalized stacks in the context of derived algebraic geometry. But first of all, we will see, how to employ homotopy theory to define stacks. And then this allows us to generalize the notion of a stack to, the infinite categorical level in a more conceptual way. So maybe if you recall classically, so the idea is, so let me just mention classically. So in the classical setup, you can define stacks like a category, stacks as a category fibered in groupoids over some other category C. Okay, so classically you can define something like this. So what does it mean? Very roughly speaking, if you have a stack, for instance, X like this, so X can be seen as a category fibered in groupoids over C. So C is your category, and each fiber here is a groupoid. Very roughly speaking. Okay, of course, there is also a gluing data. So this is a kind of a, so for any such thing, you can assign a certain presheaf, but there is a gluing data. You should be careful. And in this talk, we are going to see actually this gluing data, the descent condition, can be encoded by using homotopy theory. So our aim is somehow define stacks as homotopy sheaves. Okay, therefore this consists of actually two steps. First, you need a presheaf. You need presheaf data like this. So somehow we will consider the category of presheaves from some category C. So it's some arbitrary category right now to groupoids. Okay, so we will discuss it, groupoids. And then to do homotopy theory, we need a model structure. So somehow we are going to see that exists a model structure on that category, which essentially allows us to do homotopy theory. And then by using these two structures, this local to global data turns out to be a kind of a homotopy sheaf condition. Homotopy sheaf condition. So descent condition can be encoded like this. Therefore, we need to analyze this category and then how to define model structure on that category. And then we have a kind of an equivalent definition of a stack as a homotopy sheaf of groupoids. Okay, so this is our general approach. So let's see. Let's start with some terminology and our setup. So as you see, so the key ingredient is groupoids. So let me just recall this some elementary notions. So groupoids. Okay. So when we have groupoids, it means we have a category in which all morphisms are isomorphisms, right? So this is a groupoid means you have a category in which all morphisms are isomorphisms, right? So this is a groupoid essentially. But what is, there are some properties that we are going to actually investigate. So essentially, if you consider the collection of groupoids, it has a structure of a two category. Okay, so the collection of groupoids has a structure of a 2 category. Okay, so essentially what does it mean? So 2 category is a higher category, right? So it's kind of on top of the objects and morphisms, we have 2 morphisms, right? So we have some additional type of morphism. So very roughly speaking, I mean, if you're not that much familiar, but here 2 category means we have some objects, okay, collection of objects, and the mapping space, you know, between each object. But now this mapping space itself has a structure of a category. Okay, in general, in the usual category, right, category theory, this has a structure of a set, but now this is itself a category. Therefore, it has objects and morphisms, and there are, you know, compositions, horizontal, vertical, and many big list of axioms, let's say, but very roughly speaking, this is the essential idea. So we consider this thing. This is the 2 category of groupoids. Okay, this is our notation. So objects are groupoids. Okay, groupoids. And we have one morphisms. So these are categories. So the maps between categories. So we have functors, right? Something like this. And we have 2 morphisms in the structure. So somehow you have 2 functors like this. And you have a natural transformation between them, right? This is your two morphisms. So more or less we have structure. I mean, this is some essential 2 category we are going to be interested in. So what kind of properties we have? Properties. For instance, this category is in fact a model category. So it has a model structure. So this one has a model structure. Okay, so what does it mean, model structure? This is a structure you need to do homotopy theory, actually, right? So essentially it consists of, I mean, you need to introduce, you know, weak equivalences, fibrations, and cofibrations in that category. Somehow these are 3, you know, distinguished classes of morphisms satisfying big list of axioms, but essentially you need to introduce these morphisms. And in that category, I mean, I say category, but in this 2 category, for instance, weak equivalences for this, for instance, you have F, C, D. This is a weak equivalence in groupoid. This is weak equivalence if it is essentially okay, it is essentially surjective and fully faithful. If F is fully faithful and essentially surjective. Okay, so what? Yeah. Yeah. And I don't know. So let me mention this fibration as well. So this F is called a fibration if okay, if it is like surjective on morphism. So let me just okay, for each object A in C, and we have morphism in the image like this. In D, there exists an object B in C and a morphism F in C such that, you know, the image of this f is exactly phi, right? Sorry, so many f's around. This, let's say, f, right? Okay. Phi, okay, something like this. So therefore, it is like we have A, we have FA, and we have D. So this is given, and somehow there exists B and this assignment. Okay. Fine. Oh, something like this. Okay, good. So anyway, so we have a very nice model structure on this two category. What else? Then we can discuss. So this is the first property, let's say. And I mean, it's like you need to choose three collection of morphisms, right? Yeah. Uh-huh. Uh-huh.
In this case, it's tensored and enriched over itself. Defining more sophisticated notions of a model. Or you
Mm-hmm. Yeah.
like this is a model structure on the underlying category, such that the enrichment avoids the canonical gives this the structure of closed.
Okay. Uh-huh.
It's groupoids, they're all invertible.
They are all invertible. Uh-huh. Yeah, okay. Thank you. And what else? Let us discuss homotopy limits. Okay, homotopy limits in that category. So actually, this will be very useful when we try to describe this descent condition. Okay, so let's see. Here, yeah, cofibrations are like, I mean, here fibrations are, you know, surjective on morphisms. So these are like injective on objects. So the maps injective on objects. Okay, cofibrations. Yeah. So once you know these two. Yeah. In general, once you know these two. So let's see some notation. Let me first introduce. So we just, so this notation, you know, as usual. Let's say this is our the category of finite ordered sets. You know, so we have this one. So we define a cosimplicial object. So when we say a cosimplicial object in C, so we mean the following. We mean a functor. So I use this notation. Okay, something like this. And the image, so we have this image, you know, just like this, n simplices, right? And then we can define a cosimplicial diagram. Find a cosimplicial diagram like this. So for this cosimplicial object, of course. So as you see, it's like, if you know n simplices, you know this guy. So therefore, defining this is like knowing the collection of all of these n simplices. So therefore, we have this usual picture. So this is your zero simplices, our maps, coface maps, and we omit codegeneracy maps. So diagram goes like this. Okay, the cosimplicial diagram. So there are, of course, usual, for instance, DINs. So these are cofaces, and we have some notation SIN. These are codegeneracy map. Okay. Okay, so for this diagram, we can discuss homotopy limit. So let's see. Okay, actually, this is, so let's discuss its homotopy limit. So we use this notation. Is itself a groupoid, okay? Of x naught is a groupoid where, so let's see, the objects are, so what are the objects? Objects are pairs like this, okay? From zero simplices and one simplices, okay? Pairs like this, and such that, so H is a map between these two, let's say, vertices. I will sketch some picture and you'll see, and satisfying, and we have two conditions. So this is identity X and E12H. Okay, when I sketch some picture, you'll see actually what we are doing here. So this is your object X, like this, and H is something like this. This is your H, okay? So H1, D11 means actually this is this inclusion, and this is the other inclusion. Let's say this is D, let me check, D11X, D01X, okay? So this is your simplicial diagram, and also, okay, this direction is your code degeneracy map, like this, and of course, you have this one. Okay, so let me just this D220, D11X. These are some standard diagrams, but let me just be careful about my notation. So we have something like this. These are possible inclusions, right? And likewise, there are three possibilities for H. So let me use this one for this H, and this one, and D02H. Okay? So this is essentially what we are doing. And if you look at this, condition 1 is here, actually, and condition 2 is like, your cocycle condition here, this triangle. Okay? If you follow the notation, right? yeah, this exactly this triangle, right? So this is your objects, by the way, still objects. So objects are pairs, you know, like this. Now what about morphisms? So morphisms. Yeah, this is a co-simplicial diagram in groupoids. In arbitrary case in C, but here we are talking about homotopy limit in groupoids. Yeah. Okay. Sorry. Yeah, you're right. So here we start with some arbitrary C, but now I just quickly turn into the case for the groupoid case. Okay. You're right. Uh-huh. Uh-huh. Yeah. Uh-huh.
Down there you have on the right hand edge, you have
Could be, because I always confuse with those things. Which one?
The right hand edge.
Uh-huh.
Edge. The edge.
Uh-huh, yeah, this
Right
one.
Yeah.
Okay.
There.
This one, I guess, yeah, you're right. This one of them is, yeah, the upper one is simplex dimension. This is which phase you choose. Yeah, possibly, yeah. Let me see. Okay, anyway, so I guess there's some typo around. Yeah. So let me just write down the morphism here. Again, we have some arrows like this. Something like this. And as you may guess, this consists of two things. You need an actual map, between let's say vertices, right? And such that we should have kind of this should respect the relations here, right? So somehow, so let me write our diagram. So we have something like this. So as you see, so I sometimes use cophase and codegeneracy maps like a functors, So so just be careful. F and the 0, 1, x prime. Okay, this is also h prime. As you see, this one, and therefore this should commute. Okay. So these are some essential properties and definitions. And now we can discuss presheaf of groupoids. Okay. And then we define stacks actually. Okay, so the next thing will be presheafs of groupoids. And finally, we will define stacks. Okay. So let me just use this notation for this one. Presheaf. Yeah. Yeah. This is kind of what? This is. No. Yeah.
This looks to me like you could probably derive it from the models of Cartesian sections of the Roman construction.
Yeah. this is like definition / theorem kind of thing. So I use equivalently this thing. I mean, this is kind of a lemma essentially for us, but I just use it like our main definition. But what you write, so essentially we have another core construction, but now this one will be more useful for us.
Is it possible to provide a bit more why these diagrams are so?
Actually, this is really in the example we'll see. These are really what we are looking for. I mean, just like these are geometrically for us the cocycle conditions. For instance, we will see in the examples. These are really, the sheaf condition when you really want to glue two things, passing from pre-sheaf to sheaf. You need to know how things glue together on overlaps, right? There are some gluing axiom and identity axiom you should satisfy. Actually, these two guys really geometrically encode these things. Actually, we'll see. This is our intuition. This corresponds to your cocycle condition. This basically tells you how two things glue on the overlaps. We'll see in the example. So actually, we have a nice topology on that thing. So this is a site. There is a site structure on this thing. So when we define stacks, therefore we need covers. We need covers, and covers, and there are overlaps, and they should behave nicely on the overlaps. So therefore, these guys, essentially these pictures, essentially encode these cocycle conditions to glue, glue on the overlaps. So let's see. But this is not enough. So actually, we need a model structure on that category. Actually, so we essentially need to introduce homotopy sheaf condition. We need a model, suitable model structure on this category. Okay, to define homotopy sheaf condition. Okay. Actually, there exists. So fortunately, there exists a model structure. So I'm just going to introduce one of them. So this is, I mean, you can check the Hollander's paper, homotopy theory of stacks. I'm just outlining that paper, essentially. So there exists a global, which is called global model structure on this. So what kind of model structure it is? For instance, what is the weak equivalences? Okay. Actually, all of these are just object-wise weak equivalences. For instance, if you have F like this, groupoid is called weak equivalence in this category if each stage.
You mean the
What?
transformation between two?
Yeah. Oh, yeah, you're right. You're absolutely right.
So when you say free sheet, is it the transfer from
C to groupoids. Yeah.
Is it function or
Contravariant functor. Yeah. Yeah, this is a functor from C op to, yeah. Okay, so let's see one more time. So you have F and G, right? And each is something like this. And if FU, GU, okay, object-wise. Now this one for each object. Now you are in groupoids, and we know how to discuss weak equivalences. So therefore, for object-wise is a weak equivalence in groupoids. Okay, this is a weak equivalence in this thing, right? And you can actually write down. You can just study the other possibilities. I mean, exactly like this. So you just want object-wise fibration or object-wise cofibration for the rest of the model structure. So I just skipped that part. Yeah. What?
So you said the weak equivalences are defined
like
object-wise, right?
Yeah.
So you just look at F2 to G, the component of the structure.
Yeah, each component. Yeah.
So you get two such model structures. One is
Yeah.
the projective and one is the projective.
Yeah, exactly. This is one of them. This is one of
But
them.
then
Yeah.
Which, you need to decide whether the vibrations are defined by this or the co-vibrations.
Are you
vibration?
are you vibration wise?
So let me check.
Yeah, maybe as you proceed, it will become.
I mean, my guess would be.
So let me see. No, I mean when we say weak equivalences in this category, right? For a morphism like this.
There are two models.
Yeah, I guess so. Vibrations are also defined like this, but for cofibration we need to be careful.
Yeah. There's also the other option. If you find co-vibrations like that, then you let vibrations. Depends on what you want to do.
Yeah, I see. So anyways, actually, we don't care this one. So for our construction, this is not the thing.
Actually, if you want to do homotopy limits and stuff like that, I guess.
Yeah, actually, this is not enough. Yeah, this is not enough. We need to localize this model structure. So somehow there is a local model structure, which is the useful one, right?
It will still matter which one you start with. How you do the localization.
Yeah, you're right. But actually, I'm not going to introduce this local model structure. So there are some details. Let's say, just keep it as a black box. But the idea is somehow you need a suitable, let's say, a model structure on that thing. Let me say to give the following definition. Okay. So I just wanted to use the following definition. Okay. So let's see. So now we have a site. Okay. So we have an object like this. In this category, and this object essentially is called fibrant. We have a category. Yeah. Okay, sorry. So we have a category with a Grotherning topology on it. Okay. Yeah, sorry. So you'll see. So you have a category, and it's like just consider the category of topological spaces, right? So it has a natural, open covers and stuff, and you can see. So site is a category plus a suitable notion of topology, let's say, on it. Okay. Therefore, you can discuss an open cover for an object like this of U. For instance, U is your object, and as I said, just consider the category of topological spaces. This is really, these are your open subsets and inclusion, and this gives you a cover. It's a kind of a structure, gives us the notion of a cover of an object. Okay, and we have. So side structure not C. Yeah, you're right. So therefore, we have first of all kind of a functor, and such that the source has a certain topological structure. Okay, because yeah.
When you say have a certain topology, pull back
Uh-huh.
covers and things like that.
Yeah, there are some axioms, you know, the big list of axioms. One of them is, yeah, pull it back. Yeah, yeah. Uh-huh. For each object, for instance, so each object has an identity cover, so some standard axioms, you know, respecting composition, as you say, respecting fiber product and something like this.
Example would be
Yeah, I mean, just consider any scheme, or you have, I don't know, consider a manifold, for instance. Just consider the category of manifold. So this is your just open cover of a manifold. So your covering maps are just inclusions, open embeddings. These are your just open subset in your category. So therefore, this is more axiomatic way of saying things. So if you have a site structure, it means that for each object, you have a notion of a cover. Okay? What? Yeah, I mean, I don't know. So let's see. So let me just finish the definition. So somehow, for each cover, for instance, UI, U of U in C, okay? Because so far, remember, so far we only consider the pre-sheaf part. So in this case, we don't have any open sets or gluing properties. When we really want to glue things, we need notion of a cover for this category. So the canonical morphism. So there is a canonical notation I use. Okay, chi u homotopy limit in groupoids of this cosimplicial diagram is weak equivalence. So let me just write it down and then I will explain where. So this notation means you just consider the possible overlaps, okay, all possible intersections. For instance, this piece, and then you form a cosimplicial diagram. You consider, double intersections, Uij, and then triple intersections, and it goes like this. Okay. So therefore, if you have such a canonical morphism, so it is like to understand this image. So we just look at this diagram, and we just look at the homotopy limit of this thing, and all information is actually hidden here in each step. So remember our theorem definition. Actually, the homotopy limit, this information is encoded by just first two simplices, vertices and cocycle conditions. Just like, I mean, if you are familiar with this vector bundle business, so how to define a vector bundle, right? So you need to know, your sections, and then you need to know how section communicates to each other on the overlaps. And it's enough to use these two information, right? The cocycle condition. So if you know this thing, you can define your vector bundle, and the sheaves are just generalization of the vector bundles, So therefore, this part essentially encodes how things are glued to each other. Okay. Descent condition. This is the equivalent way of writing descent condition by just using model structures, homotopical terminology. This corresponds to, as you say, the descent condition, local to global condition. Uh-huh. Uh-huh. Oh, yeah, you're right. Maybe the right example. And actually, this, let me just finish the definition. This means the fibrant object in your model structure. And the stacks are the fibrant objects. So this is the story. So this is the definition of a stack. So stack is a presheaf satisfying this condition. Okay? What? So, yeah. Yeah. So as I said, there is some black box model structure here. And then in this.
No, so I projected model structure.
Mm-hmm. Are satisfying. I mean, these functors.
This is fibrant in the localized.
Localized, yeah. So I'm sorry, I'm really, it's a kind of a black box here. So what we are really using, they call the local model structure. But I mean, it's confusing.
Okay, but you're using that.
Yeah, yeah. For me, if you, I mean, I'm also sometimes confused with those things. So to feel more comfortable, the stack means you have a presheaf, you know, of groupoids satisfying this property. So this is basically stacks. Okay. So let me just finish the definition. So we have a site. Yeah, these are actually. So we have overlaps of fiber products or in intersections, triple, double, and somehow this. Yeah. Mm-hmm. Here we want this map to be a weak equivalence in that category. So this map, this canonical map. Yeah, yeah, you're right. So the topological, let me say, the discussion. Yeah, I mean, what? Yeah. Here, yeah, because these UIs here, it comes from the objects of C. Okay, and this data, you have fiber product triple intersection, and you want to glue these things. So therefore, you need a topology on C. Yeah, the collection of all such, you need these covers. This is where. Yeah. Yeah, in that case, yeah, some maps and the special choice of families of objects for each given object U, and satisfying certain, respecting fiber products and identity properties and blah blah blah. And particular example is if we consider the classical notion of a topology. Let's say, I mean, this is yeah, those things, those covers, yeah. In yeah. Yeah, the homotopy limit itself.
Because there is a U dot.
Uh-huh.
On the left hand side there is no U dot.
Yeah.
On the right hand side there is U
dot. So it is like you understand the original objects by looking at its cover and to understand how they glue to each other. I mean, the triple overlaps and something like this. Yeah, there is some dots, and this dotted part is this. Yeah, I don't know. Yeah, sorry if maybe I messed up. Sorry if I. No, because for this thing, since you pass through covers, you need. Morphisms. Yeah.
Like,
I see.
topology could you do this? Just given a cover.
Um, yeah, actually, term,
doesn't mean like it's anything to do with topological space.
yeah, maybe this is,
Selection of covers.
no, maybe this thing is misleading.
Just select morphisms. Exactly.
Yeah.
And it's just a set of morphisms, and then morphism between morphisms are selected inside C without selecting. I mean, they're not selected. You just select morphisms. Yeah, exactly. So you say for an object, this collection of morphisms, you have a choice of that. It's the stable, the full bag, and some other conditions. How the hell is that a topology? Right here, but it's called recursive topology.
Yeah.
Same category with covers. It's with the notion of cover for each object. You select some morphisms.
Sure.
Bunches of morphisms. Yeah, I'm just saying it. Let's get
Yeah, could be. Maybe I should. Let's say in quotation mark. Yeah. The point is, yeah, somehow we need a reasonable choice of covers somehow to describe these things. And this is called Grothendieck topology when you have such a covers. And yeah, usual covering, covered by open spaces notion is just particular case and choice, something like this. Okay, good. So let me just finish this definition. So somehow if you have a site, so a presheaf, so we have a presheaf of groupoids, is called stack, is a stack. If it is vibrant. Okay, so essentially stack is you have a presheaf, some functor, from C up to groupoids, satisfying this covering condition. Okay, so let's see an example. I don't know how much time do I have, by the way.
10 minutes left. I can go to
10. Okay. Yeah. Okay. So let's consider the following construction. Let's see manifolds as stacks. Okay, let's do this, and let's apply this definition. So the manifolds as stacks. Okay. Okay. First of all, instead of C, I just use a category of Cartesian spaces. So particular choice for C here. So this is the category of Cartesian spaces. So what kind of category is this? So we have objects. The objects are open subsets of Rn. Okay. And the morphisms are just smooth maps. Okay. Okay. And it has a natural site structure. So you can really turn this category, to a site by just introducing, your covers like this. So that's the site structure. So we just introduce open covers for which so every intersection of those open covers are either empty or diffeomorphic to Rn. Okay. every intersection of those opens, let's say, is either empty or diffeomorphic to Rn. Okay. So if you somehow introduce this kind of cover like this, this gives you a side structure of that category. Okay. So we have a manifold, for instance, like this. From the category of manifolds, we pick a manifold and we define the following functor Fm like this from this Cartesian, the category of Cartesian spaces to actually sets, but this sits inside groupoids. Okay, and so like this on object wise, for each u it sends you know, by using the maps into M. Okay, C infinity UM. And also, what about the maps? For instance, you have U and U prime. For instance, you have map like this. And as you may guess, U prime to FMU. So if you pick some row here, it sends to row composition F. Okay. What? Uh-huh. Yeah, these are like our charts. I mean, what?
So the cover has to be a collection of maps, which means
Uh-huh.
they are charts.
Uh-huh.
Opens
Opens.
to
Yeah. Like this. Uh-huh. So therefore, any manifold can be defined by its, you know, the chart-wise cover. So this is just our choice. So let's see. Okay, good. So this is our pre-sheaf data. But what we want, we want the second part, right? Somehow we need to compute the second part. And how to do it? So let's see. So we need to show. Oh, by the way, what is the canonical map here? Yeah, any question? Uh-huh. But yeah, because we have n manifold, so it's covered by a, you know, charts, and our source is, you know, diffeomorphic to Rn. So this essentially gives you, you know, maps from Rn to M. So this is your chart. Okay. So this means we have some Rn, some map M. So the collection of those things gives you a chart. Yeah. Yeah. So somehow we want to realize our, you know, spaces in terms of all possible, you know, maps into it. So this is what basically, you know, tells us.
You don't require them to be.
Yeah, I mean, yeah, sure. It's more general than that. All smooth maps. Yeah, sure. So what is this canonical map? So let us try. Maybe before that, what is this? What this thing corresponds to in that case, right? Let's see explicitly. So homotopy limit of f u dot. Okay. So it is like, I mean, as we see before, it's a groupoid itself, right? It has objects. Remember, these are pairs, but here the objects are like families. Let me use row i's from each cover, such that on the overlaps, they are the same for all ij. Okay, so by just using the theorem in this particular case, this is a groupoid whose objects are collection of these maps. These are like, you know, from each cover you have row I, and on the overlap, you know, they coincide. Okay, your objects are like this. And the morphisms are, in that case, just identities. Okay, so therefore this homotopy limit turns out to be a very simple groupoid. Okay, I mean, you can check, I mean, go back to original, you know, theorem / definition. In this particular case, objects turns out to be these maps satisfying this property, and the morphisms are just identities. Okay, so what is the canonical map? Because what we want, you need this map, right? It should be weak equivalence. Okay, so let me just write it down. So this canonical map, essentially, so what is this? So we have some row, let's say, row, some map C infinity U to M, right? It should map to here, right? Row i's on each cover. So what is the family? Family turns out to be just the restriction of the original one. Okay, something like this, and it satisfies automatically this condition. This condition is trivial because row is globally defined on U, right? So this is your canonical assignment actually. So you need to show that this assignment is actually a weak equivalence. Okay? But in that case, actually, this turns out to be an isomorphism, since this particular choice, okay, this functor itself is a sheaf. Therefore, all of these data glue together properly. So no problem. So because this is a sheaf. Okay. So therefore, this canonical map turns out to be an isomorphism, in particular a weak equivalence. So therefore, this tells you that this one is a stack. So for any manifold can be seen as a certain functor like this. Okay. Smooth maps. Here, these are smooth maps. Oh, which one invertible? Here? I mean, no. So let me think. I guess so. Yeah. Yeah, it's just sets. Any set can be seen as a groupoid. You know, objects are the elements itself, and the morphisms are just identities. Yeah. So you map to sets, and any set can be seen as a, let's say, trivial groupoid. Okay. Yeah. No, I mean, which one? Uh-huh. No. Yeah, this is so sorry. I mean, yeah, this is. But there is no, non-trivial function. These two, functions like that. Okay, there is no non-trivial function connecting them. I mean, this is the idea. Can you see? Okay. So I don't have that much time. Just maybe just quick remark, and then maybe another example. Maybe you may check this one. You can, for instance, define classifying stack of G bundles. Okay, it is like we define BG as a functor from cart op to groupoids, okay, which assigns, on each object, it acts like this, BGU, and this BGU itself is a groupoid with a single object, okay, groupoid with a single object, and the morphisms are like this, maps from U to G itself. G is some Lie group, and if you are familiar with these, construction from physics, this is like your gauge transformations. Okay, but this case is a little bit tricky when you define homotopy limits. Actually, there will be more relations, not like this, but there are other details. But somehow this turns out to be by just assigning suitable site structure and etc. By following the same proof, you can see that this turns out to be a stack in that sense. Since I don't have that much time, maybe a small remark. So as you see, let us go back this definition. In this definition, there is no particular reason to work with groupoids here. You can work with infinite groupoids, okay? Because this homotopy limit is also, meaningful in infinite categorical setup. If you just rewrite exactly the same definition, but instead you use infinite groupoids, this gives you essentially the definition of, let's say, higher stack. Okay. Yeah, this definition you can just change. You just allow higher morphisms, infinite tower of equivalences, let's say. Instead of this one, you can choose just infinite groupoid, right? Here you still have a very meaningful definition of a homotopy limit in infinite categorical setup. And this kind of definition gives you, higher stack. Okay? If you play with this source category, you can define schemes, drive stacks, but more or less, these definitions, use this functorial approach plus this kind of descent data. I don't have that much time to discuss those things, but also once you define these spaces, higher spaces, you can do, I don't know, symplectic geometry on these spaces, or Poisson geometry on these spaces. And these are called drive symplectic geometry or drive Poisson geometry. But this definition can be generalized in an infinite categorical setup. Also, this is the general idea. Okay, so maybe I should stop here. Thank you.
Any questions for Kadri?
Also, combine these two, do you get a stack of G bundles, G over manifold?
Yeah. This classifying stack of G bundles, or even you can cook up principal bounds of flat G bundles, combining. Yeah. You just fixed M. You have a fixed base manifolds, for instance. I don't know. Yeah.
I guess you can replace G with kind of vector you want, like
Yeah. Yeah. Hook up, basically.
I guess the question would be more, can you use FM and DG together to talk about G bundles over M?
Yeah, this is.
M maps from M to VG. Based on maps.
Oh, I see. Yeah. Because the proofs are always, follow the same. Yeah.
Also, we can think of FM and DG as objects in the tissue.
Yeah, sure. Yeah, objects are maps, functors, contravariant functors from C to groupoids. But the question is how to introduce gluing data to do this, because in general it's very messy, even if this still maybe looks complicated. But comparing the other methods, this approach is relatively more tractable, because this object is very well known, maybe not infinite categorical version.
But you also recover the classical theory.
Yeah, classifying. Sure. Also, as I said, the flat bundles and everything, you can recover those things as, this is your classifying stack.
All this theory still works with topological groupoids?
Topological, yeah, what do you mean by saying topological groupoids? You mean you have some additional structure? Or
Lie groupoids, for instance.
yeah, this is really there is a very non-restrictive thing. It's a very loose condition on G. G is here. Just that, I don't know. Here is you may take a Lie group or anything.
The most general construction context where you have some higher stacks. You just require G to be a group object.
Yeah, group object, for instance. Yeah.
And then you can run basically the
same thing. Yeah. And group objects are you can.
Just a curiosity, do you know why people in algebraic geometry is interested in homotopy theory of stacks? Because when I hear the word stack, it's most often from people in algebraic geometry.
Yeah, I guess the main issue, especially when you discuss derived stacks. So these are very, there are several motivations. One of them is, I guess, actually two geometric motivation. The moduli space problem. For instance, when you quotienting things out, for instance, you just consider some quotient space. Okay. For instance, you have a manifold, you have some moduli space of some differential equations, whatever. You just quotient by a Lie group action, something like this. But this quotient, the resulting space, turns out to be very bad. Okay, this may have no structure, maybe just a structure of a set. So the resulting, after this quotienting operation, the resulting space, fail to live in the same category. So you need something more general. So, or the other problem. Yeah, kind of. Or the intersection problem. Maybe you intersect two things, right? They may intersect badly. So bad intersections and bad quotients. So these operations generally give you some objects which may not in your category, so the resulting object. But if you are working with more general setup like this, the derived stack, for instance, the intersection, you use derived intersection, so you automatically end up with a stack. Maybe it's not a manifold, but it's a derived stack. So there are some categorical problems. Some categories, do not have enough limits, colimits, or something like this. By just passing this infinite categorical setup and then infinite categorical objects, let's say higher spaces, you can deal with those cases. And also you can define, these are not singular objects, for instance. You may consider a geometry on a singular object. So how to discuss a symplectic geometry on a, manifolds at a singular point, right? So singularities, bad intersections, and bad quotients, let's say. Very roughly speaking, these are the main motivations: intersection problem, quotient problem, singularities, yeah.
Very parallel
Mhm.
question, which
Mhm.
makes sense. Is there a slogan relating sheaves and stacks? I don't know which one is more general. I mean, sheaves are like Boolean specs for algebraic variety.
Yeah.
Stacks are more general, or is there a slogan between sheaves and stacks? General.
Yeah, these are particular sheaves actually, right? Sheaves, I mean, in general, for instance, just consider classical algebraic geometry, right? So scheme, for instance, right? Scheme is a particular sheaf, actually, right? From category of commutative K-algebras to sets, right? So you can play with source and target categories. For instance, we are now here. We just generalize these things to groupoids, two categorical level. We introduce two morphisms, and this assignment actually what we call stack, right? So it's a particular choice of, let's say, I don't know, this is a particular sheaf, and you can keep playing the same game. I mean, instead of groupoids, you can consider infinite groupoids, and this kind of sheaf, will give you higher stack. But if you think this is not enough, if you really want to change your local model, because here these are algebras, K-algebras, your spec A is your affine scheme, for instance, you can just use some gradings here, CDGA, in negative degrees, commutative differential graded K-algebras. Now your ring, your function, the structure sheaf is kind of a gradation. Anyway, so this is called drive stack, for instance. So these are some special construction of sheaves. Yeah, sorry.
Can you example examples? How do you choose your colors?
Which one? Here?
Choose colors in those
Oh, yeah. Yeah, in this examples, yeah, it's a little bit tricky. Yeah, in this case, your ideals, spectrum, here you have spec, and you localize. I mean, drive stacks are okay, not locally look like spec A's, but at least you have some map like this, spec A. So if you have a drive scheme, let's say, it means that at each point you have a affine cover like this, spec A. Okay, and if you want to shrink this cover, you can just localize this A. By using localization, you can shrink this affine cover. So we use specs actually, maps like this. Okay. Hmm? Yeah. I mean.
My question would be, do you have give the examples like
Uh-huh.
maybe the questions were so
Mm-hmm. Uh-huh. Yeah. Sure. The simplest one is, for instance, you want to compute the critical locus of a function, the basic problem, critical locus of a function. So what is this actually? For instance, you have f on some regular function like this, okay? What is the critical locus of this thing? You have a manifold. M is manifold, really, an actual manifold. This is your cotangent bundle. This is your df, right? Section. So the graph of a section, right? So you also have a zero section. So any manifold, can be embedded into its bundle like this, right? This is your zero section. This df is some other section like this, the graph. And if you really want to understand critical f, you need to understand these intersections. But the same problem, bad intersections. Classically, you cannot resolve this problem. I mean, yeah, but by using this drive intersection business, this thing turns out to be some kind of stack. Not a classical space, but a drive stack. Because you use drive fiber product, and this is not enough. You have more structure. We know that this is symplectic. There is a symplectic geometry on this thing. This is, in this drive symplectic geometry language, this is zero symplectic. I mean, every smooth categorical discussion fits into drive setup in a zero level, on the zero level, thing like this. Anyways, this turns out to be -1 shifted symplectic, which is not visible by just using classical techniques. Or you can compute, I'm not that much familiar with those things, but Gromov-Witten invariance, by using the stacky constructions. This critical locus is very related to any kind of gauge theory or something like this. And you may discuss Poisson structures, Poisson geometry on those things, which is related to quantization program. So there are some geometric, naturally, if you have something singular, something problematic, by just passing to this drive setup, somehow you can deal with those things. Yeah, sorry. Yeah. Logic, I don't know, number theorists, use some other purposes. What? Topos stuff, yeah. There are also topos theoretic foundation of physics or something like this, more logical discussion. Why we need to use topos to formalize quantum mechanics, for instance. There are details. I mean, I don't know. There are some fancy stuff. Yeah. Yeah.
Okay, yeah.
Why not? Actually, this is topos.
But there's a very classical construction as a category of sheaves on site of a topos, which can be used to show that the axial choice is independent.
Yeah.
So you can build a topos ZF is valid, but choice is not.
Yeah.
And that's also using the basic idea of like sheaves or some.
Yeah, topos somehow, gives us some alternative logic system at the same time, which allows us to, declare two things, are true at the same time. Very useful for quantum stuff.
So this also studying these maps by translation, understand objects like the motivation of this stuff. Okay,
Yeah.
so let's thank
Okay. Thank you.